Okay. Hello everyone again. I'm Andrei. I'm part of Neon EVM. I'm a senior Rust engineer there. And tonight, I'm gonna talk to you a bit about Neon EVM. First of all, what is Neon EVM? Neon EVM is a Solana program implementing the Ethereum virtual machine. And we built this project because we want to exploit the benefits from Solana, like parallel execution, low gas fees, and high transaction speed, in order to allow developers who already have Solidity smart contracts to deploy them directly on Solana inside Neon EVM and be able to reuse their existing code from Solidity. Of course, we also support all well-known Ethereum tools and also provide an Ethereum RPC, compatible RPC, where you can, the user sees an Ethereum chain when interacting with it, but behind it it's still Solana. We have been live on mainnet since July 2023, and of course, apart from the Solana program, we have a whole infrastructure around that Solana program to make it work, at least easily for our users. So first of all is the EVM Solana program, then is the proxy server, which is a very important component because basically when you interact with the RPC endpoint, of course the RPC is not part of Solana, it's a separate web service where you send your send transaction request, for example, and proxy analyzes it, packs it into a Solana or more Solana transactions and submits it to Solana for execution, and also collects the Solana receipts and extracts Ethereum data from those receipts. And another important part that the proxy does is Neon transaction emulation, because as my previous speaker showed, Solana has to give all the account inputs for a transaction before actually executing it. Even if you have an inner call in a Solana transaction, you have to know all the accounts from all the inner calls that will be used in that transaction. And Ethereum, of course, does not require that. So we basically we have EVM implemented in two ways. First, as a Solana program itself with the same code base. And secondly, it is also part of our proxy server API, where you can call it through a web service, and that web service implementation will trace all the Solana accounts that are actually used by our implementation, and will provide them as input for the real Solana transaction that will be built. The Tracer API component is also a very big part of our system. And is responsible, for example, for calls like debug trace transaction, where you want to replay a transaction from the past. In Ethereum, you can use this. You can do this because Ethereum stores historical data, but Solana doesn't. Basically, you cannot answer a question easily in Solana, like what is the state of an account at a certain slot in the past. So how we do that is that Solana has plugin system. They are called Giza plugins. There are some small Rust libraries that you hook into the validator, Solana validator, when you start it. Those Giza plugins add some custom logic to the validator when the transactions run. We store all those transactions and account changes into a database in our system, and then we use that database in order to query it when we want to replay previous Neon transactions. Neon Pass is used to bridge Solana SPL tokens on Neon EVM because, of course, since Solana SPL tokens are the equivalent of ERC tokens on Ethereum. And of course, we can use them very easily in Neon EVM because we are on top of Solana. Neon Faucet is a DevNet faucet that we can use to give our developers Neons to work with. And Neon DAO is used to coordinate all mainnet updates on our system. Okay. As I said, this is our ecosystem and what we support at the moment. We support all the dev tooling that people are familiar with. I myself use Remix a lot, for example, for deploying and debugging transactions on Neon EVM and seeing that they behave the same as the ones on on the real Ethereum chain. We support the known wallets. Of course, apart from our native bridge, Neon Pass, we also support the bridge. And this way you can exchange any token from any EVM compatible chain on top on Neon EVM 2. We also have 2 block explorers. Neon Scan is very similar to the Ether Scan. Actually, I think it's built by the same team. Okay, we have 2 proxy operators because our proxies can be run by anyone. And this is it when it comes to our infrastructure. Let's talk about a bit more about the architecture. So we have a DApp frontend that interacts with an RPC endpoint, Ethereum compatible RPC endpoint that is the Neon proxy. It submits to it an Ethereum-like transactions. The proxy, as I said, emulates it first, collects the Solana accounts that need to be used to build that Solana transaction, and submits it to the Solana node. The Solana node has the Neon EVM program inside it. The Neon EVM program executes the transaction, and then proxy also analyzes, as I said, the Solana receipts in order to collect the Ethereum metadata from it. This is maybe the most, one of the most important slides because it's the structure of the Solana accounts that map all the Ethereum chain state. Let's start from the Neon EVM program. It's only one. It's the Solana program containing the Ethereum virtual machine in the data field of that account. And from this, we have a hierarchy of program-derived addresses. What program-derived addresses are? They are a concept specific to Solana, and they are basically some Solana accounts whose addresses are derived from the Neon EVM address and only can be modified by the Neon EVM program. So there is ownership relationship between them. And let's take each field of an Ethereum account and see where it's stored. For example, if you have a normal Ethereum account, of course you have a nonce for it, you have a balance, and this is stored in a normal Neon account like this one, in the data field of a Solana account. And for example, when you submit a transaction that is a simple transfer on Neon EVM, it will just access 2 Solana accounts for each balance. Basically, they are called balance accounts. It will access 2 balance accounts for those Neon accounts and do the change in the balance. The interesting part is how contract data is stored, because for a contract we have to store the bytecode of the contract when you deploy it. So we have a special contract account for that. And we have to store the storage slots. The Ethereum virtual machine stores the contract's data into the some storage slots, which is basically a big hash map for each contract itself, by itself. And the Solidity bytecode, high level, it looks like it has variables, but behind the scenes all those variables get compiled down to storage slots. And we have an optimization. Some storage slots are stored in the same contract account here, as part after the bytecode itself of the contract. And other storage slots are stored in their own Solana accounts, and we have quite complex program-derived logic because we need to be able to map the addresses of those of those storage slots to the Solana accounts themselves. I won't go into details now, but it's maybe the most complex part of our account logic. And basically, if we have balances, nonces, the code of the smart contract and the storage slots, we can store the whole Ethereum chain inside the Solana account model. Okay, now this is the thing that makes this project complicated. As you know, Ethereum transactions can be big from 2 points of view. The size, they can, for example, Go Ethereum, I checked recently, it can process Ethereum transactions as much as 1 megabyte in size, theoretically at least. And on the other side, Solana transactions have a fixed maximum size of only 1,232 bytes. So very, very small. And we need to somehow be able to execute a very big Ethereum transactions using very small Solana transactions. And how we do that? Apart from that, there is another restriction of Solana transactions. They have a fixed number of compute units. Basically, the gas from Ethereum world has an equivalent in Solana in compute units. One Solana transaction can execute at most 1.4 million compute units, and I think the maximum gas limit for a block in Ethereum is 30 million gas or something like that. They are not one-to-one because, for example, our Ethereum virtual machine, for doing a basic operation in Ethereum, it can run a lot of compute units on Solana. So there is no one-on-one mapping between these two. But basically, we cannot store Ethereum transaction inside the instruction field of a Solana transaction. So the first change we have to do is to store the Ethereum transaction inside the Solana account itself. So basically when we submit a Solana transaction to the Neon EVM program, one of the input accounts will contain the transaction itself for the Ethereum virtual machine to execute. And the second magic thing that we have to do is iterative transactions. Basically, the EVM doesn't have enough time and computing resources to execute the whole Ethereum transaction inside one Solana transaction. So how we do that? At the moment, we serialize and deserialize the EVM state between iterations of the same Ethereum transaction, and we let the EVM continue execution from where it left. So basically we have to store all the changes that the EVM does during execution, because you also have to be able to revert them. EVM has quite complex features when it comes to how much you can revert of a transaction compared to Solana, where it's something like if anything bad happens, all the transaction fails, you cannot recover from anything. And in case of iterative transactions, we commit those changes only in the last iteration if everything is successful, and otherwise we could revert some changes. And that's why, for example, all the changes that we do, like setting a storage slot or incrementing the nonce or incrementing the balance, we are storing them as a list of changes into the EVM itself, and only at the end we commit them to the chain or maybe just drop them completely. Okay, and of course here it's the thing that I talked about, the fact that you have to give to the Solana transaction as input the list of Solana accounts that contain the states of all Ethereum accounts used in that transaction. Okay, about parallel execution, basically if you have, this is the difference between Neon EVM and Ethereum. If you have two Ethereum transactions that, for example, transfer some funds to two different people that are unrelated to each other, the two transactions, of course they will be executed in parallel, because this is how Solana works. This is actually why Solana requires you to declare all your accounts beforehand, and also to tell if they are only read or also written in that transaction, because if it doesn't see any data race between the two Solana transactions, it will execute them in parallel. And we are striving to create Solana transactions that are as decoupled as possible in order to allow Neon EVM to run more transactions concurrently. And okay, this is an incoming feature that is not, it's specific only to Neon EVM, but it's not very EVM centric. Basically, because Neon EVM is a Solana program, and Solana programs can call each other, of course, we want to be able to allow people to call Solana programs directly from inside a Solidity smart contract, let's say. It will not be easy, will be very limited, but it can be done. And basically, how we do that is that I think you know about the precompiles of Ethereum. We have some additional precompile addresses that are actually accessing Solana specific features. For example, you can also deploy an ERC20 contract on our network, and we have some predefined ones. But How we implement ERC20 on our side is by using the SPL token library behind the scenes. So basically there is a precompile in our bytecode, in our Neon EVM implementation that delegates to the SPL token library. So basically ERC20 is only an interface to SPL token in case of Neon EVM. Okay, so this was overall my presentation. I think it was very technical, but I hope it caught your interest at least a bit. If you have any questions?
Hi.
Hello.
In case this transaction wants to access some storage slots, let's say, do I have to know the exact storage slot for, let's say I want to execute a transaction that modifies some state, do I have to know storage slot in advance to specify it as a
Solana account input, yeah.
Yeah, and also I guess if you could just can validate this, but if two transactions are accessing the same storage slot, my guess is they cannot be executed in parallel, right? So
Yes, they won't be able to execute in parallel because Solana won't allow that.
yeah, but if I want to have some transaction that wants to alter the state, I have to know the storage slot as a user, or does that Neon relay solve that problem?
Anyone can call Neon EVM a Solana program directly, but it's very low level. It has some very low level operations that are very hard to interact with as an Ethereum developer. And that's why the proxy component, in this case, first emulates the transaction and basically executes the transaction itself as an API call, and it uses actually the Solana RPC endpoint to retrieve all the Solana accounts that actually are used in that transaction and see if it can emulate it successfully. And after it emulates it, it will know already all the accounts that it needs. And yeah, you're right. It will not be able to execute two smart contract calls that access the same storage slot. And actually, we are working on making this very granular. So even if you access the same smart contract, but the storage slots are different, you should be able to run them in parallel.
Yeah, cool. Yeah, thank you. That answers my question. Yeah.
Welcome.
Questions? Okay. Thank you, Andrei.